Well, it's time to get back to MOSFETs. Now that we have a good understanding of MOS electrostatics, we can revisit our virtual source model and see if we can make it a little bit better. So you'll recall that we developed a simple two-piece model for the transistor with a simple expression for the linear current, a simple expression for the saturated current, and then by introducing an empirical FSAT function, we could smoothly connect the linear and saturation regimes. Okay. The model is summarized here. It begins by describing current as proportional to charge times velocity, and then we describe the charge in this very simple way. Above threshold, it's minus Cox times Vg minus Vt. Below threshold, it's 0. All right, we know we have a much deeper understanding of mobile charge versus gate voltage now, and we can use that understanding to improve this model and really make it a very significant improvement. So you'll recall that below threshold, the mobile charge goes exponentially as e to the q Vg minus Vt over mkt. Above threshold, the charge goes as minus C inversion, which is a little bit less than Cox, times Vg minus Vt. Okay. Now, one of the things that we're going to need to do is to treat both subthreshold and above threshold in one smooth and continuous way. So just as we introduced an FSAT function to smoothly go from linear to saturation region, we need to find some technique to smoothly go from this subthreshold expression to this above threshold expression. But first I want to take a little bit of detour and just talk about subthreshold. We're familiar with these IV characteristics and subthreshold, how we plot the transfer characteristics on a log plot. We know what subthreshold swing means. We know what the off current is. We know what the on current is. Now, if we look in the subthreshold regime, which we could not treat in our earlier model because we assumed there was no charge in subthreshold, we now know that there is charge there, and it goes exponentially with gate voltage. We expect that the current will be proportional to the charge, so we would expect that the current is proportional to e to the q V gate minus V threshold over mkt, and we know that m would be 1 in a fully depleted ultra-thin body structure. So let's look at the subthreshold swing. So physically, we can see that the drain current should go exponentially with the surface potential. And we know that the surface potential is related to the gate voltage by introducing this numerical factor m, which is always 1 or greater. Now, we could take the log of this drain current expression. When we do these log plots, we plot log base 10, so that introduces a factor of 2.3 here. We could take the slope of this log current versus gate voltage. Well, we could use the chain rule. The first part would be the derivative with respect to the surface potential, which we can take right here. And the second part would be the derivative of the surface potential with respect to the gate voltage, which we can do because we know the relation between the gate voltage and the surface potential. If we do that, we find that this slope, this we would call the subthreshold slope, it's 1 over 2.3 kt over q times 1 over m. Normally we express this as subthreshold swing, which is 1 over this slope. So the subthreshold swing is 2.3 m kt over q, and that is normally expressed in millivolts per decade. If we put m equals 1 and t equals 300 k, we'll find that that subthreshold swing is 60 millivolts per decade. That's as small as it can be unless we switch to completely different physics. Typically, it's a little bit bigger than that. So we have this expression for subthreshold swing. It's always greater than or equal to 60 millivolts per decade. Typically, in a good transistor, it'll be less than 100 millivolts per decade. And we discussed earlier when we were talking about transistor metrics why subthreshold swing was so important. One reason is it helps minimize off current. Another reason is that it controls how much voltage it takes to go from off to on, and that really determines our power supply voltage dynamic power goes as power supply voltage squared. So it's important to keep that small. It's important to keep the subthreshold swing small so that the VDD can be as small as possible. Now, sometimes people will ask, why is the subthreshold swing greater than or equal to 60 millivolts per decade? Well, it's really going to happen any time that we have a transistor that is based on the principle that the probability that an electron can hop over a barrier is e to the minus barrier height over kT. That's a very fundamental thing. We make a transistor simply by pushing the barrier up and down with the gate voltage. Since our barrier is based on this thermionic emission of carriers over a potential energy barrier, we inherently have a minimum subthreshold swing of 60 millivolts per decade whenever there is injection of thermal equilibrium carriers over a barrier. Now, there is also a relation between the off current and the on current that it's important to be aware of. The off current goes exponentially with Vg minus Vt. The off current is measured at 0 gate voltage. The on current goes linearly with gate voltage minus Vt. The on current is measured when the gate voltage is the power supply voltage. So if we were to put these two relations together, we would find that there's a relation between the log of the off current and the on current. And this relation is very fundamental, just comes from the physics of how MOSFETs operate by manipulating energy barriers. If you take actual data, take transistors, note their on current, measure their off current, and plot them on a plot, you'll see this relation. The on current is plotted on a linear plot. The off current is plotted on a log plot. It obeys this characteristic relation. And, this is one of the challenges in device and circuit design. If a circuit designer needs a little bit more on current because we want speed that is a little bit faster, it's easy to increase the on current. We just lower the threshold voltage. But that will necessarily lead to an exponential increase in the off current, which may or may not be able to be tolerated. All right, so let's go back to the virtual source model. So we now have a better understanding of mobile charge versus gate voltage, but we have it in two pieces, subthreshold and above threshold. We need to continuously go below threshold to above threshold. Well, one way to do that is to do a numerical solution, and that in fact is done sometimes. Another way to do that is to look for an empirical way that smoothly goes between the two. So here you see a function that was introduced many years ago that actually does the proper thing between the two limits. If we look at this expression, and if we look at it below threshold, and simply simplify this expression, recognize that log of 1 plus x is about x when x is small, and that'll occur when Vg is below threshold, then we can see that this expression reduces to an expression that says that charge is proportional to e to the gate voltage minus threshold voltage over mkt, and that's the right thing. Now, if we compare that to the expression that we developed, it's not quite the same, but in practice, it's close enough. The pre-exponential factor is not as important as the fact that we've got the exponential factor correct. If we look at this empirical expression above threshold, we can throw away the 1 in the log 1 plus x, and we can see that that expression simplifies to minus C inversion Vg minus Vt. So we get the correct expression above threshold and nearly the correct expression below threshold. So it's a good empirical way to smoothly connect subthreshold to above threshold. Now, the MIT version of the virtual source model uses a little more sophisticated empirical function just to do a little bit better job of treating the numerical solution to this equation. We, of course, introduced Dibble because the threshold voltage in this expression depends on the drain voltage. But it's true that, I've said that in strong inversion, you can't bend the bands much over 2 psi b, but you can, in fact, bend them a little bit over 2 psi b. So there's actually a different threshold voltage that should be used below threshold and above threshold. And that's accounted for by introducing some additional empirical factors and an additional factor alpha, which is another empirical factor, which doesn't vary much from transistor to transistor, but just helps us fit the proper numerical solution a little bit better. So now we have what I would call a level 1 virtual source model. The first version I called the level 2 virtual source model. The difference in the level 1 model is that it has a more sophisticated treatment of the charge versus gate voltage expression, so that we can use this model to compute the IV characteristics both above threshold and below threshold. We have the same set of very physical parameters in the model. Now we have one more empirical parameter. So it's still a relatively small number of parameters, most of which have strong physical meaning. Okay, so with this extension, the virtual source model actually does a remarkably good job of fitting the measured IV characteristics of modern, very short channel transistors. However, we have to view the high field saturation velocity, the VSAT term in this model, as an empirical fitting parameter that we adjust to fit the data. And mobility we have to view as another empirical fitting factor that we adjust to fit the measured data. Okay, but we're going to see later in the next unit that we can actually attach physical significance to these parameters. We generalize the definition of mobility and saturation velocity in a way that they make physical sense at the nanoscale. And then this, again, it returns the physical basis to the virtual source model. So let's summarize. Using this semi-empirical model that we developed for the mobile charge versus gate voltage, we've extended the virtual source model so that it now treats subthreshold to above threshold continuously, linear to saturation region continuously. This model now produces excellent fits to the measured characteristics of very short channel modern transistors. But our physical understanding of what mobility and saturation velocity mean at the nanoscale is still unclear and needs to be clarified. That's what Unit 4 is going to be all about. Now, before we move on to Unit 4, in the next lecture, I'll just recap some of the important points that you should take out of this rather long unit. Long but important unit.